Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so it's a pleasure to have Mohammed Naveed speaking again today. So Mohammed is a student at the University of Illinois at Urbana-Champaign, and today he'll be speaking about Android security.
Thank you, Sani, for the introduction. So today I'll talk about our work on Android device driver customization and how the security of the phone is reduced during this customization process. This is joint work with my colleagues from Indiana University. So Android has more than 80% of the global smartphone market share. There are more than 1 million apps on the Play Store. And yeah, the good thing about Android is that it's open source. And all of our observation is based on this open source nature. And yeah, this paper, in what we show in this paper, is one bad thing about open source. It's just because of the open source nature. So what happens is that because the Android code is open source, the manufacturers customizes the Android to support different hardware or to support or to give different functionalities. For example, they have different apps, their default apps, they provide different functionalities, so they can just somehow get better phones than their competitors. And they do need to modify driver always, because for example, if they want to have a camera from a different vendor or any driver, any device from a different vendor, they need to write their own drivers for it. And yeah, so for that reason, they need to heavily customize this both at the kernel layer and the application layer. So how this works is that Google first releases their Android source code to these vendors. And then Google gives some time to these vendors because before releasing it officially. So Google releases their phones with the bleeding edge Android version, but they give some time to the other vendors so they can also put the state-of-the-art Android in their phones. Typically this time is something like 6 months. So vendors do add new applications and drivers to the kernel layer, and there was a paper at CCS that showed that the preloaded applications leak system capabilities and sensitive information to malicious apps. And Android, AOSP stands for Android Open Source Project. So since 2009, there has been 19 official Android releases. So vendors need to customize very frequently, and for every different phone, they need to customize the version that is released at that time, like the latest Android version. Yeah, before talking more, I'll just introduce the Android architecture. So Android is built on top of Linux kernel, and then on top of Linux kernel there are libraries, and there is Android virtual machine that is actually a modified form of Java virtual machine, and then these are C libraries. And on top of this layer is the application framework that provides different services to the application layer, and then on top of this application layer, developers can write their applications. So they do add, vendors do add applications at this layer, system applications at this layer, and they do heavily modify the Linux kernel layer also. We observe that there are no changes at this layer, or very minimum changes at framework layer. So as you know, the device drivers work on the kernel layer, and drivers communicate with the apps through the framework layer. So this customization process should not degrade security at both the framework layer and the kernel layer. So actually, if you are familiar with Android permission model, what happens is that the permissions are checked at the application framework layer, and then after checking the permissions, they are enforced at the kernel layer. So somehow, if the app can bypass the application framework layer and the kernel layer, just talk directly to kernel layer, for example, by just writing C code. Like in C code is somewhere here. I mean, they can just talk to kernel without going through application framework layer. So then they can just bypass permissions. So they need to, like, if they modify something at the kernel layer and there, so they need to make sure that this is consistent with kernel layer. So the customizations that are done at the kernel layer, they customizes different things. So we analyzed different phones for like what type of customization have been done, and on Samsung Galaxy S3, what you can see is that 43% of the customization in the kernel are being done for in the driver folder. And this architecture is they are also drivers, but they are drivers like for processors, for GPU, and these type of things, which we do not consider in our study because we cannot exploit them. This 20% is the other changes. I mean, they do it for other purposes. And on Samsung Galaxy S2, you can see that there are even more driver changes and less remaining changes. So this just means that at the kernel layer, they heavily customizes the drivers. And at the framework layer, they do not customize much. I mean, pretty much is the same. So how Android security model work is that Android security model is built on top of Linux user and process protection. So every app on Android is a user. It is assigned a UID, and then it is protected using Linux user isolation. And every app can just access the data that is in its own sandbox. It cannot access the data of any other app. And if application wants to access system resources, for example, camera, Bluetooth, NFC, it needs to ask for a permission at install time. When you install an app, it will ask for permissions, and at that time the user agrees, and after that the app have these permissions. So what happens is that at the install time, when you give an app permission for some resource, then an app is granted permission and it is assigned to the corresponding Linux group. So there will be a group, for example, for GPS, and then it will be assigned to that group. This is how they check if the app has permission at kernel layer. So resources on Android need to be protected both at the framework layer, because at the framework layer it checks if an app has the permission or not to access a resource, and at the same time they need to enforce it on the kernel layer, because at the kernel is where the resource, the device node exists, device file exists, driver exists. So these two needs to be consistent with each other. So this is very challenging task. If you modify anything at the kernel and then make sure that it is consistent, is very challenging, because they have just 6 months to customize the OS before Google officially releases it, and it's very difficult to do it properly. So they just don't care about security. They just and yeah, as we observed in the study, the driver programmers don't have security expertise. They don't care. They just customizes it, and then they just release the phones. And there is no documentation provided by Google to do this whole customization process. The vendors have to do it on their own. So to study this, like this whole problem systematically, we have developed an approach, and then we study a large variety of these security hazards that are caused by driver customizations. So I mean, just to make sure, these terminologies are a little confusing. So by phone, we mean the mobile smartphone, and like any smartphone, and the device actually means the hardware on the phone. For example, camera is a device, GPS is a device, and device node or device file, we mean an interface for a device driver. So every device in Linux has a corresponding file. So by this we mean this, like a device node, we mean that file. So for example, for camera they will have another file, for example dev/video 0. Yeah, so every device has a corresponding file in Linux, and then we have other files, for example logs and node files, even node files, so we call them device related files. So how we measure the whole like security of these customized phones? So what we do is we compare the protection level on the customized phones to the corresponding version of Android open source code. For example, if a phone has an Android version 4.03, then we compare the security of this version to the Android open source project, that is we use it as a reference of the same version. So here the assumption is that we are not saying that AOSP, oh sorry, this is an error, this is AOSP. We are not saying here that AOSP is the best, has best security. What we are saying is that this customization process should not degrade the security of the Android below what AOSP is providing. So we check if the vendors degrade the security below what the Android original source code is providing. So the high level idea is that we need to automatically identify the Linux files, that is like the device node files that corresponds to different devices. For example, camera will have a device node in the Linux dev folder, and we need to identify which file corresponds to camera, which is a non-trivial task. I will explain like why is it non-trivial. And after we have done that, then we need to compare levels of protection. We just see the permissions. For example, if it is publicly readable or not, and we check the permission with the corresponding file in the AOSP. So if the customized file has a different permission, then we say that it can lead to a security hazard. It is possible that it does not, but it is also possible that it can. So like if we detect this permission change, it might not lead to a hazard, but in some cases it can. So for example, in Samsung Galaxy S2, camera device is publicly readable. Like any app can read camera device without any permission. So it's publicly readable. Yeah, I'll show you attacks also, how we exploit that and carry out attacks. So like it does not need to be publicly readable. It should be just readable by the root and the apps in the camera group. So this is how the customization flow works. If you want to take a picture, you go through this manager, and this manager will just it will check permission, and then it will link you to the camera service. But how it actually, this is a virtual link. How it happens is that it first talks to a binding device. This binding is just a device, is just a driver through which this app will send an inter-procedural call. So whenever an app wants to communicate with this service, it needs to send a message through this device binder. This is virtual link, and this is how it actually works. So then it talks to this camera device through this binder, and then this goes down like this. I mean, it can talk through like this framework layer permissions, and now you can see if there is another app that is like native app, which means if you have written it in C, then you, if it is written in C, that means that you have bypassed the application framework layer. If you have written it in C, you can just access the libraries directly, and you can just bypass this whole permission system and just talk to the camera. So the whole thing is that this permission is being checked here, but it should also guarantee that this file is not readable publicly. If it is, then you can just go like this with just bypassing the framework layer and just read the camera file, just get access to the camera file. So there are many challenges to study this problem like on a large scale. So correlating the devices to the corresponding device node is hard. For example, NFC device, so NFC stands for near field communication. You can, yeah, and so it is like one device, and the name of this device on Google Nexus 4 is like this, and on Galaxy S2 is this, and it varies on every device, and we don't have any idea what it is without knowing something about this. I mean, so this was really hard how we figure out this. So we created a tool to do this this mapping. Yeah, and like depending upon vendor, this can be arbitrary. Like it does not depend upon anything. So to study this problem in a systematic way, we developed this tool that we call Addicted. Yeah, it stands for Android Device Customization Error Detector. So it has two components. One is device miner that finds out device nodes for a device, and then it has another component that we call risk identifier that check the corresponding device nodes with their counterparts on the Android source code. So this is how it looks like. This is the complete design of Addicted. This is smartphone, and the smartphone is running an application that we call test runner, and then it has our dynamic analyzer that will that I'll explain later. But what happens is that we have test case. So test case is just like take picture. I mean, if you want to see the device node for camera, this test case can be just like take picture. And this reference test case is that we need to write a complete app to take picture. So this reference test case just means that it is a complete application, but it will not take picture. So all noise that will come out of it, like, okay, let me explain it another way. So what happens is that we have this test runner, and so test runner will run this test like take picture, and dynamic analyzer will analyze all the system calls. So the hope is that if we analyze a system call, then one system call will touch the file device nodes, and from there we will pick out that this file is related to this device. Now the problem is there is a lot of noise, there are many processes running. How we find out that this device, like this call, should correspond to this device node. So for that we have this reference test case, which is the same app, but it does not take a picture. So then we do this test thing and analyze it again. So and then here we just filter out the noise, and we do it repeatedly, like so many times until we get constant. So we are sure that the device node that we are getting is just because of the test case, that is like take a picture, that is related to the device that we need. So at that point we add it to a database, and after that, so now as I have shown you that even at this point we just know that this test, like this device node, put it in the database, is related to camera. But then it can be a completely different device on AOSP, like the name can be completely different. So we also fingerprint the system calls for this device, and we create a fingerprint that will and then we find identical fingerprint in AOSP for a file. Then if we have identical fingerprint, that means that these devices are doing the same thing. For example, if two files have identical fingerprint and this one was camera, then they both corresponds to camera. At that point we are sure that these two files correspond to same device, and then we correlate the permissions and see the permission, what's the permission level at in AOSP and what's the permission level in customized OS. And after that we just report it, like say that it is a customization flaw or not. So what LCF stand for is likely customization flaw, because it might not be a customization flaw, it might be some false positive, but we output all of them. Any questions? Okay. So yeah, device minder is just like it traces operations on Android to identify related Linux device files. So static analysis here, like to do the same task, is very hard because the code is written in both Java and kernel is in C, and also there is no tool, no static analysis tool available that works. And dynamic analysis, if you want to do that, then it requires extensive instrumentation in the operating system. So what we did is we wrote our own dynamic analysis tool. So what it does is that so when we run this test, and when the app wants to communicate to this device, it goes through this channel. So when it comes here at this point, we know that the app wants to communicate with this service, and now this device, we instrumented device binder, like we added code here, and then this device binder will actually launch the tracer, that is like strace. So this application, when it is attached to any process, it will log, it will record all the system calls generated by that process. So we attach it to these system processes, and we also attach it to the application, because sometimes this application might access directly the kernel and it might not go through here, so we attach it to here also. And yeah, this is where we attach it, and then we records the all the system calls, and once we remove all the noise and everything, we will get a file descriptor for this file, and then we find out that this file is related to this device. So we do this type of lightweight dynamic analysis, and as for tracing we use strace. Yeah. So this is the test cases that we run for different devices. We run it for camera, NFC, audio, radio, external storage, GPS, and they need these permissions. If you want to access these resources, you need these permissions, and like these other, like frame buffer, you cannot even access it. So frame buffer is actually, it stores your screen, whatever appears on your screen is stored in frame buffer, so you cannot access it, like it's very dangerous, but still there is a device node for it, and same for these other devices. Yeah, and then we do these type of test cases to test each device. To remove noise, we do like extensive differential analysis and see, like so we run test cases again and again, such that we get a constant constant intersection of all these test cases, which means that these nodes actually corresponds to the device and they are not because of some noise. So after that we have this risk identifier which just compares with the reference. So for example, this is one device and that is on a customized phone, and this is other device that is in the reference. So the reference permission is like it's not publicly accessible, and here you have publicly accessible. So this is oh no, sorry, this is not publicly accessible, it's 0, and this is publicly accessible. So this means that this is a customization flaw, which means that this allows any app without any permission to read this file, which we do not want. So we did this on 3 different phones, Galaxy S2, Grand, and S3, and we found these customization flaws. That is, in Galaxy S2 we can access the camera node. Both, this is front camera, this is back camera, both of them are publicly accessible. Same for Galaxy Grand, and input touch screen. So this is another vulnerability that we discovered, that is whatever you touches on the screen, it's like it is logged, and this should not be publicly readable, and this is also publicly readable. And there is frame buffer. I mean, as I showed you, like frame buffer should not be accessible by any application. It stores everything that appears on the screen, and in this Galaxy S3 this is public, yeah. And so I mean all of these vulnerabilities allow very high impact attacks, and we developed 3 different attacks based on these issues. And so our adversary model for these attacks is, there is like these malicious apps running on the phone. Like we assume there is one app that is running on the phone and the intention of that app is bad. Like it can be any app. For example, if Angry Birds want to do this attack, they can. I mean, if anybody wants to do an attack, they can. And yeah, and all these apps that we develop, they do not have root permissions, and they also do not have a permission to use the device. For example, if I want to take a picture with these apps, they do not have camera permission. So we first developed the touchscreen logger. So our tool Addicted found that dev input even2 file, like this is even2 file, this is public on Galaxy S2, Samsung Galaxy S2, yeah. And many other phones have this problem, and Galaxy S2 is like was the flagship phone of Samsung. This was the phone which like gave them the break up, like, so like millions of people are using this phone. And it's not just because of like just limited to this, and this is like this problem is valid for many other phones also. So we exploit this vulnerability, and we can log the screen without any permissions. So if you can log the screen, then I mean so you know how your phone, where your keyboard is on the phone, right? So then you just need to fingerprint like this position, like XY position corresponds to A, this position corresponds to B. So I mean whatever you type, any app can steal this data. So if you type your password, they can log it, and yeah, again without any permissions. And then we have a camera attack that allows you on Samsung Galaxy S2 that allows any app to take pictures without any permissions. So like I mean your phone can take pictures, you will never know what's happening. And so for the camera attack, the attack is non-trivial, because if we have the camera, it wants to take picture, this is a camera app, we need permission checking. It needs to talk to this camera hardware abstraction level, and then this is like how you talk to driver, and then in the kernel layer it talks to driver, and after that you can just talk to the hardware. So we tried this approach because this camera driver, I mean, we have all the permissions, like it's publicly accessible, but this way it was hard to figure out the protocol. So the phone keep rebooting again and again, so we didn't know what to do. So what we did is we wrote our own app, and we put the complete this library. This is like the open source driver. We put it in our app as a native library, and then we just talk directly to the camera driver. So this is also possible, but it would have taken more time or something. So another we exploited the frame buffer issue, and now we can take screenshots. And if you can take screenshots, that pretty much means that you can steal whatever is shown on your screen, which means everything. Like you type your password, pictures, anything. And this is again because of this file is publicly available. And yeah, for this app we just need SD card permission, so we can store the screenshot. So now I can show you the attacks. We have attack demos. So this is the touchscreen logger attack. So you can see that this app is running on the phone, and we will just show you that it does not have any permission. If the app has any permission, it will show up here. We just show it does not have any permission, and now you launch this app, and you can see this is actually our server, like adversary server. You can see it's getting the location, pressure, and everything that's displayed on the screen. So you get like all the coordinates on the screen. Yeah, we have just blinded it because of when we submitted the paper, we didn't change it. Yeah. Yeah, so this is our touchscreen logger attack. So this next is our screenshot attack. So again, we show that this will just have SD card write permission, so it can just change SD card, because we need to store somewhere the screenshots. And now you see screen captures. There is no screen captures. This can happen in the background also. For the demo, we wrote this app so we can show that we started the app and everything. Everything can happen in the background without user interaction. So this is taking screenshot periodically. This app is taking screenshot periodically. Now you open it. It has taken all these screenshots without any permission. And screenshot, like there is no permission to get screenshot. Screenshot is like very dangerous. They don't have any permission to take screenshot. Yeah, so it just goes on and it shows this. And yeah, we have this final attack, which is very interesting, that now it can take pictures. So again, it does not have any permission. It does not have any permission. So this is our attack app. Oh, it's YouTube. It's not. I don't know what happened. Yeah. So there is just coin showing that we are taking image. Yeah. So we just started the app. Is it visible? Yeah. Okay, I'm not sure if you see it, but he put the coin and then it took the picture of the coin. Yeah, and this is like all without any permissions. So like these are very high impact attacks. If you can take pictures without any permissions, that's very dangerous, and that's also on flagship phones. So then, I mean, this is just like on 3 phones. Then we did a large scale measurement study to find out if how widespread this problem is. So for this we collected 2,500 images approximately, and they corresponds to like 288 distinct models. So some of them are like for different upgrades and like different updates for every model, but we have 288 distinct models and 240 and 2,500 images. So I mean, Samsung provide these images. They upload all their images online, so we were able to download it from there, and the rest we download from like these other third-party websites. So you can see this different distribution of Android version. The most the most phones has Android 4.1.2, and some has 4.0.4, and this is just a distribution of the Android versions. So we did a wide analysis on all of these images, 2,500 images, and we find that 53% of these images contains these likely customization flaws, and like they belong to a variety of phones because of these images, and then 40% have video vulnerability, which means that 40% of these can take pictures without any permission. And then we also discovered that other LCFs, there are other LCFs that we discovered that might or might not be a problem. I mean, it needs to be studied in detail, but we discovered there are like 28 issues. Input, there's like just one node that corresponds to input, and for video there are 5 different nodes that we discovered, and frame buffer is standard, like just FB. So there were like 1290 images have these LCFs, 952 images has a video issue. Yeah, and some has input and some has these. But you can see these are like widespread, and our attacks were possible. So our like camera attack is possible just because of this. So on 952 images, that can be like something like on 100 models, there's like millions of phones, you can take pictures without permission. So this is like the geo-distribution, like how these are distribution throughout the world. So each image has a code, like if this image is for China, then they had a code like CHN. So from that we figured out that, so in Chinese phones I have most LCFs, and less in US, less in, yeah, maybe this is NSA. NSA has a role here also. I'm not sure. Just yeah, but for some reason we find, I mean, this is like maybe on the same device models that is distributed in China, it has different LCFs than the same model in US. So different device manufacturer, like different carriers like AT&T and these other China Mobile and T-Mobile, they also customizes these OS images, and that is we found out that in the like from the Korea they have most. So model with LCFs means that they can be customization flaws, but we don't know. But this confirmed means that we know that they can cause security issues. So you can see that they are like widespread, less in US but more in other countries. Yeah, so this is how different versions of OS are distributed. Most of them have 4.0.3. So the Galaxy S2 phone that we showed, it has this version, 4.0.3 or 4.0.4. So I mean, then we studied if the upgrade process, like whenever the operating system is upgraded to a new version, whether they solve this problem or not. And we find out they fix at least one this customization flaw in 53 models. They fixed all these flaws in 6. They fixed they fixed some, and then they fixed in one version and then show up again in the next version. We found 2 of those also, and they also introduced new customization flaws. Yeah. And these customization flaws are not just because sometimes they know what they are doing, but they need it. For example, for if they have a different type of camera, they need to interact with a different driver, and they cannot, so they just make it public. Yeah. So in conclusion, I would like to say that these vendor heavily customizes the phone, and that we did a first step to study the impact of these customization on the security of these devices, and these customization do degrade the security to a horrible level, and millions of phones are affected from these vulnerabilities. We are now working to write an app that will tell you if your phone has these issues or not. Yeah, but we talked to Samsung. We actually talked to Google when we found this issue. They forwarded us to Samsung. Samsung is now we work with Samsung to fix these issues. Yeah, I'm not sure if they have fixed it all, but we are working with them, and we told them that these are the issues with your phone, for ethical purposes, and in return they send us a Note 3 phone. They have a very small bug bounty. Yeah, that's all. Yeah. So do you have any questions?
Was Samsung surprised about these vulnerabilities?
I think so. Yeah, they might have thought that they are they were at least impressed. So they offered job now in Samsung research to the first author, my colleague. Now so they are really impressed. This is.
So I was wondering, so you said that there were 36 cases where the upgrades introduced these LCFs.
New.
Yeah.
Yeah.
So do you know what the geo-distribution of that was? Did you look at that? I'd be curious to see
yeah.
if
We can do that, but
if the kind of new ones introduced happen to be biased towards a certain general.
Yeah. Actually,
that would be really suspicious, right?
Yeah. Actually, we do not claim anything about this is because of the region. It might be, but but I mean this can be.
If it's introducing, that's really a bit odd. If that's biased, right?
Yes. If they're intentionally introduced.
Thank you.
Yeah. Thank you.